What is I mean what the N is? It's
Those are the natural numbers. Whoops.
natural numbers are just positive integers, right?
Yeah,
Okay. But what is P? But what is P of N in this case?
that is the power set of the naturals, which
Oh
is
gosh, I forget what power sets are.
the collection of every subset of the naturals. So stuff like the set containing 1, 3, and 89, and the set containing not 0, 1, and the set containing 50 and 30 and 69, 420 and 3, every subset of natural numbers.
Okay.
Now, even I couldn't do this on my own. I just wanted to let you think about it for a time.
Oh, thanks.
I got it from Hagen von Eitzen. That's his username on Math Stack Exchange. Posted this solution to this question. Someone else asked this question in like 2016, and it's got like 3 answers. Because finding an explicit bijection between power set of n and r is obnoxious. In a word, you would much rather show that there's an injection from r to pn and an injection from pn to r, and then appeal to a theorem called Cantor-Schroeder-Bernstein theorem that says if 2 sets have injections both ways, then there's a bijection between them. Okay. But we got to find a bijection. Okay, so how are we going to do this? We can biject the finite subsets of n and n naught, which is the naturals and also 0. So there is a bijection from PF, that's the finite subsets of n, and the naturals with 0. And this is defined by alpha of some set is the sum of k in A of 2 to the k. And I'm thinking about this this whole thing I'm thinking about in terms of binary expansions. If, say, some finite subset of n, like 2, 3, 6, we want to assign this to a natural number, this gets sent to 2 to the 2 plus 2 to the 3 plus 2 to the 6, which in binary looks something like 1, 0, 0, 5, 4, 3, 2, 1, 0. Looks something like that. And this is useful because it allows us to put every finite subset of n to exactly one natural number, where we also have the empty set gets sent to 0. Okay, we hit every natural number and we don't miss any. And so this function is bijective. All right. That's some of the battle done, because since alpha is bijective, it's got an inverse, and that inverse is also bijective. That inverse goes from the naturals with 0 to the finite power set of n. Okay, amazing. So now if we can somehow biject the real numbers without naturals onto the infinite subsets of the naturals, and then we sort of glue those two things together, we'll have a bijection from the reals to the power set of the naturals. And that's what we want. Any real number can be represented by a binary expansion. So you know how we have decimal expansions for real numbers, like there's a 0.917318445 ... This is some real number. We can represent this same real number with in binary 10110000101101 ... where each of these places represents some negative power of 2 rather than a negative power of 10. Each real number with a terminating expansion can actually be represented by an infinite line of 1s at the end, or just putting your 0 at the end. For instance, 0. So for instance, if my pen worked, I would be able to show you something. Okay, so if we have some binary expansion that ends in like a 0, 1, 0, 0, 0, 1, and then it terminates there, this is equal to that same thing, 0, 1, 1, 0, 0, 0, and then repeating ones. Similar to how 0.9 repeating is equal to 1, we can represent any terminating expansion in one of these two ways. We're going to choose the terminating decimal. We're not going to pick the one that's a bunch of ones. We're going to define a function from 0, 1 to Pn without P finite of n, because then we know that R is in bijection with 0, 1. So if we can manage this, we'll be good. So with sort of each real number being represented by a decimal, not a decimal, a binary expansion, we send a real number to the set containing all the naturals where that position in the binary expansion is 0. So if I had a decimal, if I had a binary expansion 0.101101, that's where it terminates. So this is a bunch of zeros. That is going to get sent to not 1, but yes 2, not 3, not 4, yes 5, not 6, but yes 7, 8, 9, yada yada.
This makes sense. I understand.
Okay. Then, so we've bijected 0, 1, and the infinite subsets of the naturals. We have a lot of steps to go, however. So we still have to bring R into it somehow. We know that we can define a bijection from R onto 0 infinity open by e to the x. That looks like this. So it's like woo. That bijects R onto the positive reals. That's amazing. Then we can biject the positive reals onto the positive reals and 0 by playing Hilbert's Hotel. We just shift each natural number back 1 so that we cover 0. And we also cover 1, 2, 3, 4, and so on. We cover every natural this way. And we do nothing to not naturals. This is also bijective. Then we can biject 0 infinity onto 0, 1 by just taking the whole interval and just crushing it. So we send x to 1 over 1 plus x if x is greater than 0. This will always be less than 1. And we send it to 0 if x is 0. So then zeta from R to the power set of naturals without the finite power set of the naturals, defined by doing gamma to go from R to 0 infinity, then delta to go from 0 infinity to 0 infinity closed, then doing epsilon to go from 0 infinity to 0, 1, then doing beta to go from 0, 1 to the power set of the naturals without the finite power set of the naturals, is bijective. But we can't just glue this together with alpha inverse because zeta is defined on the reals and the naturals are a subset of the reals. So we're gonna conflict with where we should send the natural numbers. But this is no problem. We can play Hilbert's Hotel again. You can say, okay, we're just gonna hide all of the naturals. But then we also have to hide what we hide the naturals in. And then we also have to hide that. But we can do all that. Oh, this is me just saying that sort of naively. Gluing alpha inverse and zeta together isn't going to work. Because if we just say we do zeta on not natural numbers, then nothing notably gets sent to the set containing all natural numbers. So we have to fix it. So I want to biject R without N naught onto Pn without Pf of n. Then I can glue that bijection with alpha inverse, since the domain and codomain will be disjoint. So our two bijections aren't going to fight with each other over where to send any elements. Does that make sense?
Yes.
Okay. How do we hide N naught? Well, if we wanted to put N naught into R, we could send N to N plus the square root of 2. But then N plus the square root of 2 would also be in R, so we have to hide it. So we'll send that to N plus the square root of 2 plus the square root of 2. But that's also a real number, so we have to hide it. So we'll send it to N plus the square root of 2 3 times. If we perform this backwards, sort of, so if we send N plus M square root 2 onto N plus M minus 1 square root 2, where M is bigger than 0, then we will have bijected R without N naught onto R. And the assumption is we do nothing to the rest of the real numbers. So we define a subset of the reals, A, by real numbers such that there's a natural number N, which could be 0, and a natural number M, which is bigger than 0, such that X is equal to N plus M root 2. That's every number that looks like this. And all we have to do is take the square root of 2 off of it. So we define phi from R without N naught to R by phi of X equals X minus root 2 if X is in A, and we do nothing to it otherwise. So then we have a bijection zeta composed with phi from R without N naught onto Pn without Pf of n. And now we can glue alpha inverse and zeta composed with phi together to get a bijection.
What exactly do you mean by glue them together in this case?
That's sort of a topology term. I used it because I thought it would be intuitive. So we take alpha inverse and zeta composed with phi. Since their domains are disjoint, they share no elements, is what that means. They do not fight, essentially, over where to send any elements.
Okay.
And their codomains are disjoint as well. So this goes on to, zeta composed with phi goes on to Pf, only the infinite subsets of the reals, so Pn without Pf of n. And this alpha inverse goes on to Pf of n. So there's nothing in here that's in here, and there's nothing in here that's in here. So their output spaces and their input spaces are disjoint. And their input spaces together, if we union these, we get R, and if we union these, we get P of n. Now to some easier ones. That was 2.2. We left off at 2.12, or that was 2.20. We left off at 2.12, so we're doing 2.13 this time. This is spoilers. Don't read this. Oh! Show that there are uncountably many irrational numbers. Oh boy. How would I do that?
Okay, well, real numbers.
There are uncountably many irrational numbers.
Let me look at my notes about uncountably many.
That means a set B has uncountably infinite cardinality if and only if the cardinality of B is strictly bigger than the cardinality of N. So the reals are uncountably infinite, for example. Do you remember how we proved that the reals were uncountably infinite?
Yes.
Something like that. And we diagonalized them. We took this diagonal and we made a new sequence out of it.
Yeah.
That's not going to really work out too well for us this time. We don't have any guarantee that the resulting new number is going to be irrational.
So irrational numbers are just any number that has no terminating end. Is that right? Is that how that works? I forget.
Irrationals are numbers whose decimal expansions neither repeat nor terminate. So some repeating decimals, like 0.3 repeating, that's equal to 1/3. Irrationals are reals where x is not n over m, where n or m are in z. It cannot be written as a ratio of integers.
So I feel like, tell me if I'm on the wrong track or not, but the easiest way to show this would be to prove that between each natural number there is multiple irrational numbers.
That's not going to do anything for us, actually. Density won't help, because Q, the rational numbers, those are also dense. Any two real numbers have a rational number between them. And as a consequence, any two real numbers have infinitely many rational numbers between them. Yet still, the rationals are countable. We proved that somewhere.
Okay, see, now I'm confused because there are more real numbers than natural numbers, but the cardinality is not greater than the cardinality of the other. Wait, what? Now I'm more confused.
Okay, what are you confused? Tell me something you're confused about.
So there are more real numbers than natural numbers, correct?
Yes.
Then how is the cardinality of real numbers not larger than the cardinality of natural numbers?
All right, I see. Because the real numbers is not just the irrationals. It's the irrationals together with the rationals.
And yet it's still countably infinite?
What's it?
The real numbers.
The real numbers are uncountably infinite.
Oh, okay. Never mind. I mistook what I thought I heard.
So R bigger than N. This actually really helps. This right here. This is exhaustive. A number is either rational or it's not. And if it's not, then it's irrational. So the reals are equal to the irrationals union the rationals.
Okay. So
we know
if we can
that this is countable.
Okay. Well, if part of it is countable, to show that the rationals are uncountable, if both were countable, then the real numbers would be countably infinite.
Yes. That's exactly it.
Since we know rationals are countable, irrationals must be uncountable.
Mm-hmm. So R is equal to R without Q. I'm gonna standardize my notation right here. I'm gonna use this slash to mean set minus. So this just means reals, but without rationals. So that's irrationals. Union the rationals.
Okay. Why would you not just use the minus sign?
That's what this Q is.
For set minus.
Because it could be ambiguous.
Okay.
A minus B could mean the set containing all elements that look like A minus B, where A is in A and B is in B. And that's not going to be the same as A without B.
That makes sense.
R is going to be the irrationals union the rationals. Okay. We know that a countable union of countable sets is countable. So if R without Q were countable, then R would be countable, since we would have a countable union accountable. That's a contradiction because R is uncountable. Proof.
Incredible.
All right, don't look. I think I have spoilers. Whoa! Okay.
Whoa, that's a lot of spoilers.
Prove that n cross n is countably infinite by showing that f from n cross n to n, defined by f of n comma n, equals 2 to the n minus 1 times 2m minus 1 is a bijection. Okay. We already know that countable cross countable is countable, but it's asked us to do this by verifying that that this is a bijection. So I just went ahead and I made a table of n and m's, and these are f evaluated at n comma m. Let's kind of see how I got there.
Yep.
To like get a handle, we need to check this is bijective, which means we need to check that it's one to one and onto. So if we let x be an arbitrary natural number, by FTA, which is the fundamental theorem of arithmetic, x has a unique prime factorization, p1 to the k1 times p2 to the k2 dot 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 times pj to the kj, where pi is the ith prime and ki is a natural or zero. So this is 2 to some power times 3 to some power times dot 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 times the last prime to some power, and these primes I'm allowing to be 0.
Why did we start using primes?
This is going to help.
Okay.
So it usually helps. It helps absurdly often to break a natural number into its prime factorization. Since p1 is 2, that's the first prime, x is equal to, we'll just replace p1 with 2 right here. So x would be 2 to the k1 times p2 to the k2 times dot dot dot. Okay. That means p2 to the k2 dot 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 pj to the kj has no factors of 2. So that's odd. And that means there is a natural number such that p2 to the k2 yada yada is equal to 2m minus 1. That's the definition of being odd. Thus, x equals 2 to the k1 times all of this, which is 2m minus 1 for some m. So x is 2 to the k1 times 2m minus 1. If k1 is a natural number or 0, then k1 plus 1 is also a natural number. So we can define n to be k1 plus 1. Then 2 to the n minus 1 times 2m minus 1 equals x. So f is onto. Okay, I've let x be some arbitrary natural number, and I have showed that there is an n and an m such that this, which is equal to our function, is equal to x. So every x gets hit by something. So the function is onto. And now we need to show injectivity. So we start out by supposing that for some elements in the domain, n cross n, f of n1, m1 is equal to f n2, m2. That just means these outputs are the same. We want to show that these two things are then equal. 2 to the n1 minus 1 times 2m1 minus 1 is equal to 2 to the n2 minus 1 times 2m2 minus 1. That's just the definition of f. Okay, again, by the fundamental theorem of arithmetic, these two guys have prime factorizations. Since they're odd, those prime factorizations do not include 2. So for some factorization, p2 to the k2 yada yada, and p2 to the r2 yada yada. So 2 to the n1 minus 1 times this factorization equals 2 to the n2 minus 1 times this factorization. Since prime factorizations are unique, that's part of the fundamental theorem of arithmetic, each pi to the ki equals pi to the ri. So if two numbers are unique, they have to have precisely the same prime factorization, which means that this has got to be equal to this up here, and this up here has to be equal to this over here, which means that n1 is equal to n2. This also means that the entirety of this is equal to the entirety of this, which means 2m1 minus 1 equals 2m2 minus 2, which is going to mean that m1 equals m2. So these coordinates are the same.
Makes sense.
All right. Let script f be the collection of all functions f from R to R. Prove that f is uncountable. Okay. Now we're cooking.
So what that means is that f is the collection of functions that give you real numbers from real numbers?
Yes.
Okay.
And we want cardinality f bigger than cardinality n. Okay. And we're gonna go with good old contradiction. If we suppose that f were countable, then we could enumerate it. We could put it in a big list. F1, F2, all the way to Fn, all the way to whatever. Okay. And now I'm going to construct an f that's different from every fi. How do you suppose I'm going to do that?
I don't know.
Well, we know that for every I, fi of 0 is a real number. So if we list all of these functions evaluated at 0, they're going to give us some real numbers. And those real numbers are going to have decimal expansions.
Okay.
Then what do you think is happening? Does this layout look familiar at all?
Vaguely. Although I don't understand how you do with that with a function.
All I need is any function from the reals to the reals. It doesn't have to be continuous, doesn't have to be like specifically positive or negative anywhere. All I need is that there is any input that's different from the rest of the functions at that input.
Okay.
So I'm going to make a function whose f of 0 is different from all of these by diagonalizing this right here. I'm going to define a function g from the digits to itself. By 9 gets sent to 0, and anything less than 9 gets sent to itself plus 1. So it looks like this. 0 gets sent to 1, gets sent to 2, gets sent to yada yada, gets sent to 9, which gets sent to 0.
Okay.
Then I'm going to define h from the singleton set containing 0 to r. By h of 0 is the sum of g of all of these things. I need to put times 10 to the minus I in there. There we go. So that this would be 0 point g of d1 negative 1, which is g of this guy right here. And then g of this guy, then g of him and him and him all the way down.
Okay. I now understand.
Then define f from, maybe not f tilde, from the reals to the reals by f tilde of x equals just x. If x is not 0, it doesn't matter. And h of x if x equals 0. Then for every single natural number, f of 0, f tilde of 0, is not fi of 0, since the ith decimal part of f tilde of 0 is not equal to the ith decimal part of fi of 0. So I've made a function that's not in the list.
Incredible.
Whoa! Okay. Oh, this one's fun. I'm going to let you think about this. Show that the smallest infinity is the cardinality of n. That is, if a is a subset of n, then either the cardinality of a is finite or the cardinality of a is the cardinality of n. Ooh, you can see some spoilers. I'll let you think about those.
Smallest infinity is n. So a is... Can you read that second line again?
Then either the cardinality of a is finite or the cardinality of a is equal to the cardinality of n.
So that is a is a sub...
A is a subset of natural numbers. That's right here.
Okay. Okay.
And I'm gonna translate these two sentences down here for you as well. What's up with this? Why is this the way that it is? I'll translate this from math to English for you. Either A has a biggest element or it does not.
How would something not have a big... Well, okay, I guess the null set doesn't have a biggest element, but that's like the only case where it doesn't have a biggest element, right?
What about the even numbers? They don't have a biggest element.
Uh, so any infinite set has no biggest number? Is that what I'm
Yes,
gathering?
that
Okay.
would be the case.
But
Still don't, I still don't know
any
what's going on with this fucking thing.
any non-infinite set has a biggest. Okay.
Okay, let me maybe put this to you a different way. Either there is a natural number that's bigger than everything in A, or every time I try to claim that some element of the natural numbers is bigger than everything in A, I'm wrong. That is, for every natural number, there exists an element of the set A such that X is smaller than A.
So yeah, either there's a biggest element or it's infinite.
Mm-hmm. So here we go. If one, A has an upper bound, A is also bounded below by 0. That is, for every A in big A, 0 is smaller than or equal to A. Thus, the cardinality of A is at most X. So the cardinality of A is finite.
Mm-hmm.
All right. If 2 gets a tiny bit more complicated. For every element A of big A, define LA to be the set of X in A such that X is smaller than or equal to A. So every LA is just the things that are smaller than A. And we're going to define a function from A to N by f of A equals the cardinality of LA. We need to show f is injective. So suppose that some inputs agree, then the cardinality of LA1 equals the cardinality of LA2. So we're considering f of A1 and f of A2. That's the definition of f right up there. Definition of LA1 is just going to be this boy, but replaced with A1. So the cardinality of the numbers at most A1 is equal to the cardinality of the numbers at most A2. I want to show then that A1 is A2. So if I suppose for the sake of contradiction, that's not the case. A1 is in fact not A2. Wolog, that means without loss of generality. I could say A1 is smaller than A2. And I can say that because there's nothing actually different about these two sets in terms of how I've constructed them. I could replace every A1 by an A2 and every A2 by an A1, and it's going to look exactly the same. So I'll just do it one way.
Mm.
Okay. So I can, without loss of generality, say that A1 is smaller than A2. Then A2 is bigger than A1. Shocker. So A2 cannot be in LA1 because A2 is not something that's smaller than A1. But if A1 is smaller than A2, then X smaller than or equal to A1 implies X smaller than A2. So LA1 is actually contained in LA2. Everything in LA1 is in LA2. But A1 isn't in LA2, and A1 is in LA1. Thus, actually, we have proper containment, that LA1 is properly contained in LA2, and they are not equal. So that actually, since LA1 and LA2 are finite sets, that implies that the cardinality of LA1 is not the cardinality of LA2, and that contradicts this up here. So A1 has to be equal to A2. That's f is injective.
Okay.
Now that f is surjective. By well ordering, hell yeah, everyone's favorite theorem, A has a least element, B. So f of LB equals 1. There's only one thing that's at most B, and that's B. Okay? We're going to show that every other natural number is hit by induction. Now suppose that for some arbitrary k in the naturals, there is some ak such that f of lak is equal to k. This is the induction hypothesis. I want to show that then there is some ak plus 1 such that f of lak plus 1 is equal to k plus 1. Okay, that's me showing that one domino knocks over the next one. So I'm going to let M, a subset of A, be the set of all natural numbers in A greater than AK, strictly. By well ordering, again, M has a least element, ML. That's like in M and it's the least one, okay?
Mm-hmm.
And for any X in LAK, X is in LML, since ML is bigger than AK. And that means that LAK is contained in LML. ML is in LML, but not in LAK, because ML is bigger than AK. So we have proper containment. LAK is properly contained in LML. Since ML is the smallest element of A, bigger than AK, LML is equal to LAK union the set containing just ML. So the cardinality of this is going to be equal to the cardinality of this plus the cardinality of this. The cardinality of this is 1.
Yeah.
By induction, for any natural number, there is something in A such that f of A equals n. So f is bijective, and so cardinality of A equals cardinality of n. Booyah, QED, proof done. That's amazing. Incredible. Amazing stuff. Prove that the set of all finite subsets of n is countable. Oh, you know what? We did this already in 2.20. Isn't that crazy?
True.
But we're going to do it anyway. Stuff we know, if a subset of naturals is finite, then it has a least element and a greatest element. So it's binary time. So let A be the collection of finite subsets of n. Define f from this set to the naturals by, we're doing the binary thing again, where we send a set to its binary representation. We need that f is injective. So we're going to suppose that two outputs agree by the uniqueness of binary representation of natural numbers, which is a theorem. Those two elements are going to agree. And then I put end of proof. Because it says countable, not countably infinite. Then all that requires is that we can inject this into n. We don't need a bijection just to prove something is countable, just an injection.
Yes.
If it said countably infinite, then we would need this to also be a surjection. Don't look at spoilers. Look away while I hide this. Or you can look.
Okay, I'm looking. Does it exist an n between 1 and 10 such that between the two of them exists m over n? Okay.
What do you think?
I can't solve this without me crying and my mom or dad yelling at me, bro. Sorry.
It's okay, so I'll turn you up a little bit so the viewers can hear. What do you think, Soda? Just give me a yes or a no.
Oh, I saw the spoiler. I'm sorry.
You saw it? Okay.
Yeah, I saw it.
That's okay.
Yeah.
Think about why that might be the case, Soda.
I feel the frustration and the tears coming. Hold on.
Dude, I'll get so many views.
Wait, m and n are a subset of z? Is that what that is?
M and n are integers.
Are integers. Oh, okay. I think not.
How come?
Because at the most granular points, unless I'm misunderstanding this, m over n is at increments of a tenth. And I believe I imagine that there are rational numbers, or real numbers, sorry, that are closer together than a tenth.
Okay. That's fair enough. Can you give me two real numbers such that nothing in this set is between them?
1.11 and 1.12, I think.
Fair enough. That sounds like it's going to work to me. The answer is no. What? 1 over 100 is real. Suppose m over n is 1 over 100. And since n at least 1, then 100m is at least 1. Okay, which means m is at least 1. So 100m is at least 100. N is at least 100. Huh? My guy. What were you on when you wrote this?
Is it possible that you at one point changed the 10 to 100?
No, I'm just gonna be very terse about this. No. consider x1 equals 0, x2 equals 1 over 1,000 proof.
You know, that seems reasonable to me.
Let A be the set of polynomials with rational coefficients. Okay. Prove that cardinality A is countable. Oh boy.
What is a polynomial again?
Something that looks like this.
Okay.
Where n is finitely big, so this doesn't go on forever.
Mm-hmm.
And is also positive.
Okay.
And these things are what?
What's your
Rational?
coefficient?
Or rational?
That thing is a coefficient and it's rational. Okay. Prove that A is countable.
Okay, so we only need an injection from that bad boy into n. That's all we want. Okay? We're going to show immediately that an is countable for every n and n, where I've defined an to be the set of polynomials of, this should be degree, n with rational, and that means the largest power of x is n.
Mm-hmm.
Okay. So if we can manage to show that every set of polynomials of degree n is countable, then we maybe do a countable union of all those. That's also countable, right? So we let n be some arbitrary natural number. I just write it out explicitly right here. An is equal to the set containing all Cn x to the n plus a bunch of stuff plus C naught, where each Ci is rational. Then define a function fn from an to q to the n. That's q cross q cross q n times, which is countable by countable cross countable is countable by fn of the polynomial equals just sending all the coefficients to the coordinate cn comma c1 comma c0. F is injective is frickin' obvious. Proof. Qn is countable by countable cross countable is countable. So there's an injection G from Q to the N to N. So G composed with F from AN to N is injective. And so AN is countable. This should be cardinality. By countable union of countable sets is countable. The union of all those AIs is countable, and that's equal to A. All right, 2.2 we already did. Look away. I've got spoilers for 2.21.
I've looked away.
Oh, wow. Okay, that's very short spoilers. All right, you can look.
Okay, I'm looking. Prove that the set of points on the unit circle in r squared, real numbers squared? Is that what that means?
That's R cross R.
Okay.
That's
Is
all
uncountable.
all the coordinates A, B, where these are real.
So the unit circle in R means what exactly?
It's these points.
Okay, so
all these green
R1
points.
comma R2.
So points X, Y on this guy. On the green circle. Those points.
Fair. I understand. Well, two things here.
Mm-hmm.
A fundamental understanding of how circles work in geometry tells me that there are an uncountably infinite amount of points.
Proof
But
by
also
just look at it.
Proof by just look at it. But also, both R is uncountably infinite, and the other R, additionally, also uncountably infinite.
Okay. These are subsets. This is a subset of R cross R.
Where's that? Where does it say that?
That's okay.
How am I to know this?
So the unit circle,
yes,
is defined as all the coordinates x, y in R cross R, where x squared plus y squared equals 1.
Okay.
So I've drawn for you an xy plane, and this set of points in green is the unit circle.
Okay.
And none of this is in it. None of that is the unit circle. Only the green.
Okay. I no longer know how to think about this.
All we have to show is that this set surjects That is, there's an onto function from this set onto R. Or equivalently, any subset of R with equal cardinality to R. In particular, cardinality of the interval -1 to 1 is equal to the cardinality of R. And we got -1 over here, and we got 1 over here.
Okay.
So what if I just squished the circle? I just crushed it onto the x-axis.
Makes sense.
So what if I defined S1 is a fancy way of saying the unit circle. What if I defined f from S1 to -1, 1 by f of xy equals x? Boom. Done. Yo, that's big and long. We got a new definition. That's why that's in blue. I did this one today. A real number, x, is said to be algebraic if x satisfies an equation of positive degree, an x to the n plus yada yada plus a1x plus a0 equals 0. So that means this, there is at least an x term. We're not allowed to have just a constant term. There has to be at least an x, where each coefficient is rational. So an algebraic number, the algebraic numbers are precisely the numbers which satisfy some rational polynomial. A number y is not algebraic if and only if y is transcendental. So the definition of transcendental is not algebraic. Prove that there are countably many algebraic numbers. This looks awfully similar to that there are countably many rational polynomials. And that's exactly the strategy we're going to try.
Let's see it.
There are countably many polynomials in Q adjoin x. And what that just means is polynomials in the variable x where their coefficients are in Q. That's just a different way of notating that. To see this, note that a function from Q to Q adjoin x by a goes to a x to the 0 is an injection. What I'm actually doing right here is I'm saying there's an injection from Q to Q adjoin x. Then I'm going to say that there's an injection from Q adjoin x to Q. And by Cantor-Schroeder-Bernstein, cardinality Q is going to equal cardinality Q of x, or Q adjoin x. So we then need to inject Q adjoin x into Q. So we're going to define a set F0 to be all of the constant polynomials. We're going to define F1 to be the set of all polynomials of degree 1. And yada yada. Fn is going to be the set of all polynomials of degree n. So Q adjoin x is going to be the union of all those fn's. The union of all the fn's is going to be the set of all finite sequences of elements of Q. The cardinality of each fn is equal to the cardinality of Q to the n, which is countable. We know countable union of countable sets is countable. So this is going to be countable. And if we take something in an fn, we can inject that into Q to the n, or to Q adjoin x by sending this sequence to a0 plus yada yada plus an x to the n, where we just send each of these elements of the sequence to that element adjoin x to its position. This is injective by the definition of equality for polynomials. Polynomials are equal if and only if all of their terms, if all of their coefficients are equal. All the coefficients on matching powers of x are equal, I mean. So Q to the n injects into this union, which injects into Q adjoin x. So Q adjoin x is countably infinite, I think. I'm pretty sure. So each polynomial in Q adjoin x has at most countably many real roots by the fundamental theorem of algebra. That means only countably many real numbers can satisfy any rational polynomial. So the algebraics, which is going to be the union of over all the polynomials of real numbers such that a polynomial is 0 is a countable union of countable sets. And so A is countable because there's countably many of these, and each of these is countable. So this union is going to be countable.
Which makes sense.
Now, a proof that there are uncountably many transcendentals. This is shockingly similar to proving that there are uncountably many irrationals. Using measure theory, okay, you don't know any measure theory, but I do now, so I'm going to flex it a little bit. If A is the algebraics, since A is countable, it's measurable and has measure 0. R without A is then also measurable, and the measure of R should be equal to the measure of R without A plus the measure of A. So the measure of R without A should be equal to the measure of R, since the measure of A is 0, which is infinity. So R without A is uncountable, since countable sets have measure 0. So if a set doesn't have measure 0, then it's uncountable. All right. Without measure theory, it's actually shorter.
Incredible.
It takes way less machinery. You know that image of the guy with like the giant ping pong paddle and he's hitting this tiny ping pong ball? That's what I just did right there.
I can imagine it. Editor, can we have that in post?
Or like, you know, this guy cutting a steak and he's got this like claymore that he's cutting this steak with. That's what I've just done. Without measure theory, it's shorter and easier. So suppose for the sake of contradiction that R without the algebraics could inject into N. Then the cardinality of R should be equal to the cardinality of R without the algebraics, then with the algebraics again, which would be also countable, which is nonsense. Contradiction symbol.
Incredible.
Should be cardinality right there. And with that, guess what?
Have we defeated all of chapter 2?
We defeated all of chapter 2.
Incredible.
That's it. We're done. Next, chapter 3.
Oh, God.
Sequences. That is gonna go crazy, go stupid, go dummy hard. Because sequences, that's where it fucking kicks up, man. I'm telling you. That's analysis.
See you next year.
It's awesome. See you in 4 months.